Hello and welcome to Advanced Inorganic Chemistry. I am going to teach you everything I know about inorganic chemistry. And if you are here, you are either forced to watch these lectures or you must be terribly bored. So brace yourself for a bunch of excitement. Alright, so inorganic chemistry. You've probably had a 2-semester course for organic chemistry, and this is where we really study carbon-containing compounds. And inorganic compounds, we no longer have any carbon, right? We're going to study something that's not carbon, like iron and aluminum. Not exactly true. So this compound here is generally considered an organometallic compound, so it can be studied by organic or inorganic chemists, and so we have an interest in this as an inorganic chemist, right? We have a metal, and that in itself makes it inorganic, and so but so all of the carbon it's everywhere here, right? In fact, we have probably more carbon than metal, but it is really the bonding that we're interested in here, and the molecular shape, and so you can already tell if you only have an organic background that this right here, this carbon to ruthenium bond, is unusual. But just basically having a covalent bond between a nonmetal and a metal is not what you were taught, right? So we're going to look into the bonding. For now, we're just going to introduce the material. And so for organic chemistry, usually we say organic compounds contain carbon, right? So the one we just looked at is definitely also considered an organic compound. But it's really not important to distinguish and label where this compound goes and who should study it, right? We have a lot of chemistry that deals with both, right? So, but just looking at definitions, anything with carbon in it is going to be considered an organic compound, and then there are some exceptions, and so they're listed here: carbon monoxide, carbon dioxide, carbonates, cyanides, and then the pure forms of carbon, the allotropes, graphite and diamond, and then of course the people synthesized or made allotrope of carbon, which are the fullerenes or the buckyballs. I'm sure you've heard of it. It launched the entire study of nanotechnologies. If we wanted to simplify this rule, we might want to argue that organic compounds are those that have at least one carbon-hydrogen bond in it, which would conveniently eliminate all of those exceptions that are listed here, all of the allotropes and these compounds, so that deals with that. But then of course we start a whole new series of exceptions, like the entirely fluorinated or chlorinated or halogenated hydrocarbons, as well as this compound here, which is urea. And of course urea is the metabolite product of the digestion in the human body, or mammals will digest the proteins they eat and into ammonia, and of course ammonia is toxic, so our liver has an enzyme that will convert that to urea, and then that can be safely excreted. This is still toxic, but it's less toxic than ammonia and less harmful, and so that's what what mammals will metabolize proteins. It's interesting that aquatic life and birds do a different kind of metabolism. The fish or aquatic wildlife will simply generate ammonia and excrete that into water, and then of course we have bacteria in the water that will convert that to nitrite. And I can't remember, there's names for these bacteria, and then there's a second bacteria that'll convert that to nitrate, and so then that is the least harmful, and it can actually be taken up by plants and as a fertilizer, and then turned into proteins again, right? And then we can consume it, or the fish can consume it, and it goes back like that. Not exactly a great nitrogen cycle, but it shows you that not just photosynthesis, which of course is part of the carbon cycle. We always talk about carbon dioxide, make a big deal out of it, and how it is cyclic and gets recycled. And then of course global warming is caused by all this captured carbon from millions of years ago. But all of these elements, they cycle nicely. And also interesting to note is that birds will produce uric acid or guano. They both have similar structures. The point is that it takes these amino acids and it cyclizes them into this interesting bicycle here that contains several of these units that used to be amino acids and proteins, and that becomes a very potent fertilizer that can be used to grow your plants, and you can actually buy guano in the store as a fertilizer. Okay, so that's just carbon, organic, inorganic. What are we truly interested in when we study organic chemistry? So you spend 2 semesters probably studying a lot of carbon-carbon bond formation. How do you do this? What reactants do you use? And also functional group transformation. So these two are important. A lot of synthetic chemists use this, and the knowledge of how do you make a carbon-carbon bond without destroying a particular functional group, or how do you turn a carbonyl into an alcohol, and so those can be very important for organic synthesis. Here's just an example of how complex something can be. This here compound shown here is Texol, and it is a naturally occurring product that has anti-cancer activity. It's found in the Pacific yew tree, and if you want to treat a single patient, I think you have to chop down like 6 of these trees. Each tree takes 100 years to grow, and so then you can only extract like 6 kilograms of your drug or something like that. The point is that there's an interest in synthesizing these natural compounds and making derivatives. And if we're going to do something like that, you want to be able to make these carbon-carbon bonds and then connect everything in a multi-step synthesis. And so it's important that we understand how to make carbon-carbon bonds and how to do functional group transformations. So these two are very important. In order to improve our knowledge of how to make these two things happen, we look at mechanisms, and then obviously stereochemistry is important for the functionality of your product, so you want to be careful with that. And then how do we study that? Well, we use spectroscopy. So you probably spend a great deal looking at IR and NMR, my personal favorite, and we're going to look at NMR in great detail. And then mass spec can also be helpful, UV vis, and there's a number of instruments that can help us determine if we've made the right product, or just analyzing what we have. So those things are very important for organic chemistry. So what is the inorganic chemist interested in, right? So we have here is an example of a Grignard. You probably studied a Grignard. And you might have even done one in the lab where you had to take magnesium filings, and they had to be shiny. They couldn't be oxidized, so that's important because you need a magnesium as a reagent. You took an alkyl halide, and this R group here can vary, and that's the beauty of it, because that R group eventually is going to transfer to this carbon here. So this ketone is going to be turned into an alcohol, and you're going to transfer this R group. So your main interest in studying organic, or this Grignard, was probably to turn a ketone into an alcohol and be able to modify which R group we have. So we do both things here. We make a carbon-carbon bond, right? And we're going to transfer a functional group. So that's basically what I was just saying we did in organic chemistry. You probably didn't really care too much why we need the magnesium, and looked into the mechanism. And then really important, you need this anhydrous ether. And I won't go unless you have really dry ether or THF. So some solvent that contains oxygen is important. And so and then so as an inorganic chemist, I'm going to be interested in what is that structure, and how does that happen, and what is the driving force of this reaction here, right? So we have magnesium here going to magnesium +2, so this is referred to as an oxidative addition, for example. That's important. That's an important step in a lot of processes. And then sometimes it's followed by reductive elimination, but not in this case. The magnesium really, it just precipitates out as magnesium hydroxide, which is insoluble, and that's part of the driving force. But if we take a closer look at this intermediate that is made, right? So this is all you're worried about. And if you look at the intermediate, it actually has the solvent coordinated or bound to magnesium in order to stabilize it, right? If you don't have the ether or a THF in there, you're not going to have a stabilized intermediate, right? So the reaction will not occur, and that's also why you have to have very dry conditions, because if water's in there, it's just going to cleave that bond. And so if you think back to general chemistry or even organic chemistry, this really doesn't compute at all, right? So we can look at magnesium. A double salt is not an issue, so you have a chloride here and a hydroxide. It makes sense because magnesium is +2, -1, and -1. So okay, fine. Kind of like alum, potassium, aluminum sulfate. You can have two different anions or counter ions in it. That's not a big deal, but it shouldn't really take on a third and a fourth ion, or even bind to an oxygen. But it does that here, right? And so this is considered a donor covalent bond. And we will be looking in how does it do this. The lone pair of oxygen donates electron density into a p orbital, and so that's what we're interested in studying this. So we are also looking at structure and bonding and reactivity and the driving forces. And in order to do so, we need to also look at spectroscopy. Very, very important. And so we have two examples here. You've seen this one already. And so the inorganic chemist is we're going to explain, we're going to try to name this, right? And we're going to look into how these bonds here, even the chlorine to ruthenium, you might consider that an ionic bond. You have a metal and a nonmetal, but when we look at the difference in electronegativity, you'll find that this is actually has a high covalent character and is not really an ionic compound. This one's very interesting. It is called ferrocene, and it actually has the cyclopentadiene. So you have 5 carbons here, and it's really it's flat. It's aligned from the side where all of those pi electrons donate electron density into the d orbitals of iron that are empty, and so this is very interesting. This was synthesized by accident in the 1950s, and it started the entire era of organometallic chemistry, which ultimately helped us produce plastics, and so I'm going to talk about that at some point. But so what do you need to do? Oh, sorry, not there yet. All right, so we're going to look at bonding and symmetry and structure and all of these things that are listed here. Nomenclature, got to have some nomenclature. We need to be able to name these compounds that we're talking about. Coordination chemistry in general refers to any metal complex that has these donor bonds, like the Grignard, but also the organometallic compound is in general considered a coordination compound. And then in the very end, I do want to look at some materials, at some silicates and boranes and some phosphate structures. So that's about it. If you want any more detail, you can look at my syllabus. This brings me to my final slide of my introductory lecture. If you haven't taken chemistry in a while, if you need a little bit of refresher, I'm going to do some review, but I would recommend that you review these chapters from your general chemistry book. If you don't have one, I recommend you use OpenStax. It's a free book, and so you want to be looking at just ionic and covalent bonding, some Lewis structures, and review atoms. We're going to do some quantum mechanics here in the next lecture, just very basic. Anyway, this is a free book anybody can access. It's Chemistry Atoms First. There's a regular one, and either one will work. You just have to find the right chapter. So chapter 3, electronic structure and periodic properties. Number 2, atoms, chemical bonding, Vesper theory. It would really help if you reviewed that, and go ahead and watch the next lecture.